Hey, and good morning, good afternoon, good evening for those of you who are doing this afternoon, great. This morning, great. I don't know if you're watching at 3 a.m. in your jammies, that's fine too. Hope you're doing well. And today what we're going to go over is a couple things. We're going to do a couple episodes for this review. We're going to try to do a vertex compensation review. We've covered vertex compensation in the past. To the tune of how to vertex for contact lenses, because obviously as the eyeglass prescription is generated in a phoropter, which is generally 12, 13, 14 millimeters away, if the doctor generates a prescription and I use that prescription, that lens power is supposed to be placed at exactly the same distance as the phoropter was that generated the prescription. If we move it too far away or too close, as in eyeglasses, 3 or 4 millimeters closer or farther, you have to have the same power, the same effective power as what the doctor generated or expected or prescribed. We're going to have to alter what we put in the glasses if it's too far away or too close relative to what the doctor generated. Contact lenses, it's obvious. Your contact lens is not at the same distance away from the patient as the phoropter was, because the contact lens is in touch. It's on the surface of the eye, so the vertex distance, or the distance from the lens to the patient's eye, is in fact significantly different, especially with contacts. We're going to go over residual astigmatism again, and then finally we're going to get into the real meat of this unit, and that is the toric lenses. Now I apologize for the lighting. I'm here in the classroom, not in my regular office, and the lighting is much different. So hopefully we'll be able to use this board a little bit, but let's share this and let's get into our how to vertex first. So this should negate any concerns that we have for the lighting. Now, we'll start with, we are going to talk about, like we did in our lab, the introduction of, if you're talking about GPs, there's 4 different ways you can make a gas permeable lens. The one that we've talked about profoundly and exhaustively is the spherical gas permeable lens. This is a gas permeable contact lens that is a single curve, spherical curve, on the back in terms of the power, and the same on the front. So if we measure it in the radioscope, it has one single radius of curvature in all different 360 degrees of that lens radially. And if I put it in the lensometer, it's going to have a spherical power. Straightforward. But now we're going to get into the last 3, and that is bitoric, front surface toric, and back surface toric. Before we do that, though, and we did that in class, and I'll have a lecture on that in just a bit, but before we do this, we have to cover our residual astigmatism. I'm not sure what that was, but that's fine. Sorry about that. So we need to remember vertexing, which we're going to get into, residual astigmatism, which we covered this semester earlier, but we really have to get down because this gets to the root of how the lens designs work. So first we're going to review vertexing for prescriptions. There's a really good website here from John Seeger with the Optician Works if you want to recover. You've learned this in ophthalmic optics with Brian and in the first year. And now we're in the second year. This should be review. If you're having difficulty with this, I need you to revisit. This is instrumental in ABO, in opticianry, in contact lenses. This is one of the big ones. This is what the formula looks like. Here, if we wanted to push something in, we have the lens, the specified lens power, prescribed power. If the doctor gives us a -10, but we move it a certain amount closer or farther, we can plug this all in and simply say, hey, the doctor gave me a -10. If I set this change in vertex from where the doctor prescribed to where the patient is wearing it, this would be 0, and so this would cancel out. So the power would be just the power that the doctor prescribed over 1, or the effective power of our lens, if you didn't have a change in vertex, would be exactly that same lens power. So if the doctor prescribed a -10, and they refracted at, say, 14 millimeters, and your glasses were at 14 millimeters from the patient's eyes, you'd simply swap in and throw the prescription that the doctor asked for. Straightforward, simple. But when we get into eyeglasses, if we move the lens, if the frame fits a little too far away or a little too close, what that doctor intended and what you're giving them are two different. So ideally, what we need to do is determine where the distance refraction was performed. In a perfect world, this would be specified. Well, it's not. I was taught in school that if it is a plus lens, you should use 12 millimeters. If it was a high minus lens, you should use 14. The user manual for the 4-opter, at least for the Reichert that I use, and it says 13.75 if the doctor is lining everything up correctly. Here, for our purposes, I'll generally specify what that what the reference is in terms of where the distance refraction was performed. It'll be 12, it'll be 13, it'll be 14, it'll be 13.75, no worries. Step 2, we measure the vertex correction for the glasses. We use a vertometer, we use a distometer. You can use a PD stick, you can use a digital measuring device, which is arguably potentially better. And what we're going to do is we're going to find the primary meridians the prescribed if there's a spherocylindrical lens. Find the power in the sphere portion of the lens, find the total power in the cylindrical portion of the lens, the sphere plus the cyl, and now we just throw it right into this formula. Pretty simple and straightforward, you would think. And then it'll tell us what the new effective power is. So essentially, let me go to the board real quick. Let's stop sharing. And the way I like to try to remember this is as follows. And again, I apologize for the lighting, if you will. But if I have a lens and we prescribed it, it's a high plus. The idea is everything should have come, parallel light will go through my lens, we converge through here, and then converge through the cornea, converge through the crystalline lens, and if all works according to plan, it comes to focus right on the back of the retina. Pretty straightforward. Now, the problem is, this is where the doctor had it. We had it vertex distance, let's call it 14 millimeters away. And if I put my glasses at 14 millimeters away, then everything should work properly. But if I take this whole system, you see where this lens is, where everything comes to a focus, it's a converging system. If I were to simply, let's put this dotted line where it's not where it is anymore, but we're going to move this plus lens, let's say closer. And in this case, contacts are easy. Unlike glasses where we have to move it farther or closer away, contact lenses by definition always go closer, and they always go closer by the entire vertex. If this was 14, the amount we're going to change it, well, the vertex distance for a contact lens is by definition 0 millimeters. So we will have moved it by 14 millimeters. Now my lens is now closer. But if this moved closer or to my right, then this also moved. It is now no longer on the retina. And essentially what that means is the old lens system came to a focus exactly right on the retina. But as I moved the lens forward, the entire system moved back. And what that simply means is my new system now no longer, if you look at it and understand converging and diverging lenses, we simply didn't converge enough. It's converging to a point behind the eye. If that's the case, that simply means that the power that I have here, if I move the lens forward, the effective power compared to the old lens, it's not enough. Plus, it's too much. Minus, essentially, it's not enough plus. We don't have enough converging power. Now, that's what that formula before did. That it tells us what the effective power is. So essentially, what's the effective power here? Well, in this case, we are going to have to calculate what this new effective power is compared to the old one, find out what the difference is, and then adjust the power accordingly. However, disregarding that gets complicated. All I want you to do for right now is understand that if I move a lens closer towards the eye, the system itself, in order to work properly, in this case, I'm going to need to add more power to converge it more. I need to add more converging power here. How do I add more converging power? I add more plus. So, in this case, if I added something where it was already converging but not converging enough, I added more plus power, that should take care of, right, add more plus to this lens here, that will allow this to converge more so that I get it right in the back of the retina where it should have been in the first place. So anytime I move a contact lens closer, whether it's a plus lens, whether it's a minus lens, it's immaterial. Essentially, if I'm moving any lens from its spectacle prescription to its contact lens, we're going to adjust the contact lens so that it is more plus than what the spectacle prescription is. And I'll show you what that looks like in a minute, but just remember that little idea. So now let's get us back up here. So now we could do all this. Interestingly enough, I teach an ABO advanced review course, and a formula. I've always been a perfectionist, but it turns out that there is an easier mechanism for this, and I wanted to share it for you, even though it's not really useful for our contact lens class. It turns out that we could instead of this fancy convoluted formula here, and where we have the power, we plug it in, we 1 plus the product of this in meters, so if we moved it by 14 millimeters, it would be 0.014, times the power again, plug it into my computer, that would tell me how much I'm off. I would find the difference between the two, and then add that to the original prescription, and that would give me my vertex power. Well, that's a little convoluted, and there's a lot of opportunity for math errors, and I want you to understand that and why it happens in the derivation. But there's also a cheat sheet, and essentially it is, if you take the power, and where D is the power of the lens in question, or in the meridian, if you square that power and divide it by 1,000, it is a good rough estimate of the amount of power change that will be required for every millimeter that you change a vertex distance. You don't have to use this every time. You can use this simple formula. So how would we do this? Well, let's use the -10, for example. If I use this formula, apply the formula, power squared divided by 1,000. 10 squared is 100. 100 divided by 1,000 is 0.10. 0.1 diopter change for every millimeter of change in vertex. So if we had an eyeglass prescription, well, I told you that the doctor prescribed it at 14, you fit it at 10, there's a 4 millimeter change. Well, you would, for every millimeter change, you multiply it by 0.1, we would have 4 times 0.1. That 4 times 0.1 is 0.4 diopters. You would have to change the power of that lens that you give to the patient in the eyeglasses by 0.4, almost a half a diopter. And so instead, since we're going closer to the eye, in our example, we need to add plus. So we would add a plus 0.4 to our -10, and so we'd get a -9.6 would be a very great approximation. So if you're doing ABO or just a rough estimate in your head and don't have a calculator, you can do this pretty well. So for example, here's an example for the glasses. If you had a plus 14 minus 2x is 180, and the vertex distance that they prescribed 13 millimeters for the in this case, and I apologize for the how it's actually set up, it's a little clumsy, but the doctor refracted at 13, you fit them at 9, so you made it 9 millimeters closer. Well, what do? Throw out a lens cross. Sphere, cylinder, axis. Remember, sphere always corresponds to the axis. So at 180, we have a plus 14. 90 degrees away, we have all of the sphere. plus all of the sill, so a plus 14 and a minus 2 is a plus 12. So we're going to vertex these individually by 4 millimeters. Well, how do you do that? Well, let's do the 90-degree meridian first. 12 times 12, or 12 squared, is 144. Divide that by 1,000, and what this tells me is for every millimeter, we're going to change this, what we prescribe, now what we fit in the glasses to match what the doctor wanted, 0.144 diopters. We knew we had it at 13, moved it to 9, so there's a 4 millimeter closer. 4 times our formula, which gives us how much we change it for each millimeter, will be change it by 0.576 diopters. And between you, me, and a lamppost, I would probably round up to 0.58. Be that as it may, in this particular case, at 90 now, remember, if we're bringing it closer, in this case we went closer, you're going to add plus. Well, we have to change it by 0.576. We're going to add more plus. So in this particular meridian, instead of a plus 12, we're not going to give them a plus 12 anymore. We're going to give them a plus 1257 to match what the doctor intended. Now, let's go over to the 14. 14 squared divided by 1,000 gives me 0.196. Again, we've moved it 4 millimeters closer, 0.0784. Well, we need to add this much more plus to my plus, so I have a 1478. And so what this simply means is, if I put it back in the lens cross, here's my sphere power, 180. 1478 goes to there. How did I go from 1478 to 1257? Well, the difference between these two is minus 2.21. So what I would put in the eyeglass lenses would be a 1478 minus 221, axis 180, and this is how I would, if I were in a testing situation, using the rough estimate, power squared divided by 1,000, here is my new eyeglass prescription that I would put in there. This was a review for you. This is not to scare you away. I want to show you how all these numbers work. You can use this formula. You can use this formula. But for the contact lenses, and these are important because the change in vertex is going to change every time. It could be 3, it could be 4, it could be 7 millimeter. Well, it won't be 7. You won't change the pair of glasses quite that drastically. But for contact lenses, we're always going to move it closer, and it's always going to be by the amount, the entire vertex distance, because they refracted at 12 or 13 or 14 millimeters. We have the vertex of 0, so there's not as much variation. And to make this easier, I will, for our purposes, allow you to use my little chart. I'll always give you a chart. And how does one read this chart? Well, when we're vertexing, if we had a prescription that was 4, I'm either going to add plus if it's a plus, or add plus if it's a minus. But if I add plus to a minus, it's less minus. If I add plus to a plus, it's more plus. So essentially, if the doctor writes out a plus 4, I would, in fact, if it's a plus 4 the doctor wrote, the contact lenses I would fit would be a plus 425. If the doctor wrote a plus 6 prescription, I would give them plus 650. If I wrote to them, if the doctor wrote a plus 8, I would give the patient a plus 887. If it's soft lenses, I've got to round to the nearest quarter, so it may be an 875 or a 9. We'll get into why we would do that later. If instead it was a minus, if it was a minus 425 that the doctor prescribed in the spectacles, if I move closer to the eye, I'm going to have to add more plus for them to see equally well, or equivalent, give that patient the same effective power as what I wanted. I won't give them a minus 425 like the doctor asked for contact lenses. It'll be a minus 4. If instead the doctor asked for a minus 7, I won't be giving them a minus 7. I'll be giving them a minus 650. And if they gave me a minus 10, I'll be giving them a minus 887. So it'll either be an 875 or a 9, depending on what we're doing, and I'll get into, most soft lenses only come in quarters. So in contact lenses, this chart, which I'll allow you access to for our purposes, this is easier to read. So let's give this one. Let's vertex this following RX that the doctor gave us. It's a minus 6, with a minus 350. Axis 180. Well, what are my total powers? My total powers are all right. Sorry about that. Let's stop sharing and we'll give this. So here we go. So here's our new eyeglass prescription. This is what the doctor gave us. They gave us a -6, minus 350, axis 180. If we put this on our lens cross, remember, sphere, sill, axis. Sphere goes with the axis. So we're going to find our 180 and we're going to simply make this a -6. This is what it would be for glasses. 90 degrees away at the 90th degree meridian, because this is an easy one. We have the entire sphere plus the sill, which would be, now to add them algebraically, a 6 and a 350 would be minus 950, 180, 90, off you go to the races. So now that we have those spectacle prescriptions, we are now going to go back to our chart here, and we are going to look at what is 650. If I look at this chart, it's a 650 and it's a minus. So I'm going to go from the 650. I'm not going to give them 650, I'm going to add plus, and in this chart it gives me exactly a -6 for the contact lens power. It's already been vertexed. Much easier to do it this way. If you understand vertexing, that's fine. I'm not going to make you do all the work for this purpose. If I do ask you to vertex for glasses, or ask you to show your work, you'll be able to do it. But in this case, that 650 brings me a 6. If the total is 950 in the 90th degree meridian, my 950 vertexes down to an 850. So 650 goes to 6, 950 goes to 850. So let's go back. Stop sharing. So my -6 will now, for contact lens purposes, let's use a different color so you can sort of tell the difference. Maybe we'll do a blue. We will no longer do that -6. The -6, actually, let me rephrase this. I do apologize. I used the wrong number. A -6 will vertex down to a -562. I hate eighths when I'm doing these, but it's 562, so I apologize. This -6 will vertex down to a -562. My -950, according to our chart, vertex down to a -850. So now, in order to give the doctor what they wanted at 14 millimeters, so we put it on the cornea, the new prescription would be sphere, sill, and axis. Well, the axis is 180, we haven't changed that. The sphere is a -562, and to get a 562 to an 850, you do 5, 6, 7, 8. It would be 862. Take off an 8, it would be -287. Take a look at this here. I've got the -562, so I'm changed it here, and then a -287, axis 180. If I give this person a contact lens that has a 562, -287, axis 180, it should give them the same effective power as this -6, -350, axis 180 in an eyeglass prescription. And that's vertexing for contacts. We can do some, I'll give you some examples for pluses and all the sills. So in contact lenses, for our purposes, what we're going to do is we'll give you the prescription. I want you to break it down into its component parameters. There we go. And then, in this case, we just said that we're going to vertex it down into -6, goes to a 562. The -950 goes to an 850. And so my new contact lens, vertex power, will be 562 minus 287, axis 180. This is the contact lens, or the closest I can either order it, make it, or get a soft lens that is close to this, and we'll show you how to round up or down respectively. This was our review on how to vertex. And we're going to end this video here because I want to break it up into chunks instead of go straight through for an hour. So vertex compensation, if you don't remember, we're going to give you more examples, and we're going to stop you right there, and then I'll see you for video number 2 for this semester, for this unit.